Excuse me, your microphone is muted, so we don't hear anything.
Okay, fine. So, okay, so hello again to the logistic regression lecture. Logistic regression is one of the oldest, say, machine learning methods. It's sort of started from regression of real values, where a lot of people know the well-known least squares, and logistic regression tried to extend it to categorical variables, where you are trying to estimate from measurements 0, 1 predictions, class 1, class 2, or maybe more classes. So first we'll start with motivation. Why, what are the assumptions, how logistic regression started, why the model that it's adopted is useful. And then we'll explain the training procedure. So logistic regression is say, proper machine learning method, in the sense that directly it estimates parameters of the classifier on the basis of the training data. But of course, we'll see that it's deeply embedded with some assumptions about the probabilistic models of the two classes. We'll explain the cost function involved, the gradient descent method to solve the training, which is the training is an optimization process. And then we'll show some examples and conclude by looking at strengths and weaknesses. So let's start with the motivation. So we know from our from lecture 1 that if we are solving a Bayesian decision problem, which is we are minimizing the expected risk, and we have a 0-1 loss matrix, so every error costs us the same, and that is 1. And if we make a correct prediction, the loss is 0. Then the optimal classifier is the one that, given a measurement, estimates the a posteriori probability pk of x. If we had the model exactly, we would not estimate, we would estimate the probability density of the posterior probability, and the correct decision, the one that will lead to minimizing the risk, is the maximum class. We can look at it as a posteriori or joint, because the difference between px and k, maybe I can write it down here, that pk given x is equal, okay, you don't see the paper, let me switch. So px given k is p, k, and x divided by px. But if we are trying to look for the argmax, then this is a constant independent of k. So the argmax of the left side and argmax of the right side is the same. So as you see in the lecture, we can go for argmax, and that's the same thing as going for the argmax x given k, the conditional probability, the probability that that class k generates x times the prior pk. And for a binary two-class problem, deciding for the maximum a posteriori is the same thing as deciding for class 1 if p1x is greater than p2x, because if p1 is that's if we are deciding between two, this is like the maximum class, then that's the same thing as p1 given x divided by p2 given x is greater than 1, and that's the same thing as logarithm of this ratio of a posteriori probabilities is greater than 0, and if it's smaller than 0, we go for class 2. If the ratio is equal to 1 or the log is equal to 0. It's the probabilities are the same. We'll make a 50% error and we can decide as we wish. The ratio of a posterior probabilities is called the odds ratio, and the logarithm is called log odds. The word odds is in English is a little bit dangerous because it's used in betting, and in different countries and on the continent you have many different ways how to express odds. People who are involved in betting, hopefully not to their detriment, they know this. So for us, log odds is the logarithm of the ratio of the a posteriori probabilities. Okay, and now we'll have a look at, I'm muting some bad guys, done. Let's see how such log odds. So we'll now be looking at this logarithm of P1x over P2x. We'll be looking at the functional form of this ratio for some commonly encountered distributions. So perhaps we do not have this P1x, P2x, but we'll have a look at how this looks like if we had it. And we'll start with a multinomial, multidimensional Gaussian. So I'll just click on a page later on to give you some idea how this could look like. So imagine this is a two-dimensional measurement space. So we are making two measurements, and the class conditional probability has these elliptical isocontours, which suggest that the covariance matrix is not diagonal. You see that for the two classes, the covariance matrices are the same. You see them, the covariance matrix is written on the right. And the centers are 0, 0, and 1, minus 5. So probably if someone asks you, draw the optimal decision boundary, you might draw it, everybody will draw it somewhere between the green and red part. But now let's go back to the formal maths, where we'll try to establish the form of the log odds. Now, the most difficult thing on this slide is just to get used to the mathematical notation, because it might look strange. And now I will spend like 5 minutes, maybe more, or maybe 10, on making sure that you do not you get familiar with multidimensional Gaussians, so you won't be afraid of it. So a one-dimensional Gaussian has two parameters, the mean and the standard deviation or variance. Now, if we look at this, let's say formula 4, 5 is the same. So let's have a look at the final part, which is E minus 1/2 x minus mu 1t inverse of the covariance matrix and x minus mu. Maybe I'll draw this bigger, but hopefully you can see this. So my first question on Friday was, how would you describe in mathematical terms this expression? How was this called? And you touch this in algebra. You can say it, you can write it in the chat. Okay, no one. So this is a quadratic form. And so x is a vector in d-dimensional space. Mu is a vector in d-dimensional space. So it's something like that. It's 1 times d. The covariance matrix is a d times d matrix. And here we have the column vector x minus mu. So all in all, this is a real number. So you can think about this quadratic form as something which takes a d-dimensional vector and outputs a real number. Now, Okay, so there's a question in the chat whether I can make the paper video larger. No, I can only write with little bigger letters. Okay, I'll try to write larger letters. That's what I can do easily on my side. The video has like it's covering the paper. Well, okay, it could be the fraction of the paper. So, okay, I'll make it, but yeah, okay, fine. So, hopefully you'll be able to resize it. Okay, so coming back to our problem, but this matrix is not any matrix because it's a covariance matrix. It's symmetric, which is written in the slides as the transpose is the same as the matrix itself, and it's positive definite, which has a mathematical notation like this. And what does it mean? That a matrix is positive definite if for any two vectors, oh, I have to make it, this thing is greater or equal 0. So actually now we know that the exponent part maps one d-dimensional vector to a non-negative real number. And then the rest are what you see in front of the expression of for the 2 pi to minus d half and the determinant of the covariance matrix 1 over and square root. These are normalization constants. So how does this, by the way, come about? So we know that in 1D, the one-dimensional Gaussian has this form. Sorry, mu squared sigma squared. Okay, imagine you have, this is ith dimension, and you would have the independent Gaussians. So then you would, if the question was, what is the probability of x1, x2, x3 up to xd, if they were independent? Well, it would be a product of such distributions, sigma 1, sigma 2, e to minus 1/2, x minus mu 2 squared, sigma 2 squared, sigma 1, and so on. So we'll end up with pi, then we'll have 2 pi, and it will be 1 over square root of to the power of d, and this thing is 2 pi to d half minus, and then we'll have e 1/2, and then a sum. This is unfortunate because the sum is like the sigma, exactly the sigma we use for the large covariant matrix. And here we'll have x minus mu I squared over sigma I squared. But this part can be written as, in the form that we have here, x minus mu I, and here we'll have a diagonal matrix 1 over sigma 1 squared, 1 over sigma 2 squared, and so on, and zeros here, and vector x there. So we can write this as pi 1 over 2 pi to d half e 1 minus half x minus mu transposed diagonal matrix D x minus mu. And so this will give us something like 1. This could be a Gaussian which looks like that or like this. These are isocontours, and this would be the mean values. And now to be able to...
One question.
Yes.
Did you intentionally leave out the sigma at the 2 pi at the first part of the equation, or was it?
Where did I? Now I'm thinking, where did I miss it? Aha. No, that's a mistake, of course.
Okay, yeah.
Here there should be sigma I. You are right. Yeah. Wrong. Good that you noticed. And now the remaining thing that is missing here is that we couldn't have in this derivation, we can't have a ellipse like that, and for that we need to rotate the space. But the rotation of the space would rotate the x and mu, so there would be a rotation here and a rotation there, actually from the other side because it's transposed, so it would be RT, and the RT dr would be our inverse covariance matrix. So we can get, so any Gaussian multidimensional could be seen as something like this. One-dimensional Gaussians get multiplied because they are independent. They have, in different directions, they have different sigmas and different means. And then to get the full general covariance matrix, there is some rotation involved, and that rotation then it rotates the x and mu's, and we get a covariance matrix. This, by the way, shows that every covariance matrix can be decomposed, and the same with the inverse. It's into a diagonal matrix and two rotation matrices, which is actually the Jordan form of the matrix. Here we have the eigenvectors, and here we have eigenvalues. So we see more in this. So from this moment, you shouldn't be scared about seeing something like that. Now, now maybe the question is, how come the determinant of the inverse covariance matrix square root is here? Well, if you look at the diagonal matrix back here, you see that the determinant is the product. This is the inverse of the covariance matrix, and the determinant is and then we have one square root of the determinant. So the determinant is the product of these sigma I squared. So square root will be the product of sigma i's, exactly like we had it here, the sigma i's. And actually the determinant of a product is a product of determinants. Rotational matrices have determinant 1, so everything works fine here. Yeah. So from now on, you are familiar with multidimensional Gaussians, and it will become useful, for instance, when we talk about PCA and LDA. Now, coming back to the slides, let's have a look at this odds ratio. So in logistic regression, we want to model the log odds. So we'll take the fraction, formula 4 and 5, and the logarithm. So first we use the rule for logarithm. Log of a product is a sum of logarithms. We notice that because of the covariance matrices of being equal, the normalization factor cancels out. We get log E and the exponent. Log of E, these are inverse functions. So we'll get only the exponent, which is quadratic form. And then the prior probability is, these are two real numbers which sum up to 1. So this is some sort of constant, the logarithm P1 over P2. So after some arithmetic, now I'll explain a little bit. I remember when I was a student, I had problems with expressions like this. And someone asked me, can you prove that this is xtax minus 2 or minus yatx minus plus x a, okay, minus y, this is t, and plus yta y. How can you prove this? Well, the best way I'm saying to look at this is that imagine that this is first some fixed z. This is actually a vector. So if you do almost, I would say that almost, so this if you ask students at say the final exam, prove this, they might have problems. But if you ask them, if you have 2, 3 vectors in this form, everybody will say this is xtz minus ytz, and then you say, okay, let's substitute for z and use the associativity. And now let's think about this as another vector, okay, minus and so on. Now look at, this is a vector, let's call it w, and you will have wxy. It will be xy, x minus xy, y. Substitute for w and you will get that. So this is the only thing that is happening here in on lines 10 and 11. And we'll see that the quadratic term cancels out. And now we have to look carefully what is unknown and what is known. So what we want to know is what is the log odds as a function of vector x. So sigma minus 1 times mu1, this is a vector. So we can collect all the vectors that are multiplying x, and that's another vector. You see, this is like the vector between the 2 centers of the Gaussian multiplied by the inverse of the covariance matrix. And these part of the product, mu1 transpose sigma minus 1 and mu1, this is a vector times vector. It's sort of like a generalized scalar product. You can look at it, or scalar product. You can first multiply the thing on the right and so on. So this is just a constant. And in the end, surprise, surprise, the log odds for these two Gaussian distributions with different means and same covariance matrix is a linear function. So one immediately starts to suspect that instead of estimating this mu1, which is a d-dimensional vector, sigma, which is d times d matrix, but it doesn't have d square unknown variables. How many degrees of freedom or unknowns are in a covariance matrix? I think you should know this. So what we are talking about is if we have a d times d matrix, which is symmetric, how many elements in the d times d symmetric matrix can we choose? So it's 37 people here. In the Czech course, there were some opinions.
I mean, you can choose along one axis only, right?
No. So if you have a symmetric matrix, you can choose here everything and here nothing, because once you've chosen that, this is defined plus the diagonal. So it's not d square half, because that would half of the diagonal would not be chosen. It's d times d plus 1 divided by 2, which actually is always an integer, by the way. So fine. So but instead of, and then mu2. So instead of estimating all of that, getting p1x, p2x, and from that making a classifier, I can go directly and estimate the w and w0. So this is d numbers and 1 number. So I've simplified my problem from estimating d plus d square half, well, d plus d, d times d plus 1's half, into the problem of just estimating d numbers, and I've lost nothing. So, and any method that would, we see that the log odds is linear. We can see here what this is. So you see the log of these two numbers change quite rapidly. So by the way, to interpret these logarithms, so if you have p1x to p2x, so if it's something like 10 to 1, 10 to 1, so in this situation, the class 1 is 10 in 11 cases, and this one would be 1 in 11 cases, so somewhere like below 10%. So the logarithm, we are talking about natural logarithms, will be something like 2.5 or something like that. Yeah. So logarithms which are like 10, this means that the ratio between the probabilities is something like e to 10, already huge numbers. And that's visible here, that there's a very short transition period. If we change the priors, that will just change the offset, no big change. Okay. By the way, if someone tells me that our log odds, so logarithm p1x, p2x is a linear function, then we'll see in a minute that the a posteriori probability has to follow something which some of you have seen, and that's this is the AX. Yeah, this is AX. So it takes this particular form. And that comes just from getting rid of the logarithm and taking into account that these two things have to sum up to 1. Okay, now another completely different model that also have linear log odds, very surprisingly. So this is the model with independent binary measurements. So the example I worked on Friday would be perhaps recognizing some animals, but the example which is in the presentation is about our favorite example of distinguishing between females and males. So we have two classes, and for binary features we could have x1, for instance. This is equal 0 if length hair is smaller than 5 centimeters, 1 otherwise. And the second feature could be x2, 0 if shoe size greater than 41, smaller, say smallest, 1 otherwise. Yeah. So it's quite likely, probably obvious, that we'll call, let's say class 1 will be women, that we'll call pi the probabilities for the first class, and kappa will be for the second class. So pi 1, this one refers to feature, not to class. So pi 1 is the probability that women have hair longer than 5 centimeters, and 1 minus pi 1 is the probability that women will have hair shorter. Kappa 1 the same for men, and 1 minus kappa 1. 1 minus kappa 1 is the probability that men have hair shorter than 5 centimeters. Pi 2, kappa 2, same thing for shoe sizes. Now, the first thing we have to understand here is the expression 20 for the feature vector x given the first class can be explained, can be written down as this product. So the first thing we will look at is Formula 19. Formula 19 is like a compact way of writing an if statement. So xi can only be 1 or 0. Either you have the binary feature or you don't have it. So if xi is equal 1, then 1 minus xi is 0. And the second part, something to 0 to the power of 0 is 1, and it's sort of multiplication by 1 is like no change. And pi I to the power of 1 is pi I. If we switch 0, the first part is switched off, and the second one is true, 1 minus pi I. So that's for one feature, and then we do it over all dimensions. So for D binary features, and it's easy to create x3, something like maybe neck length. I'm not sure what is the neck length, what is the average neck length for a man. I don't know, 35 centimeters. So maybe we can say, so it will be neck. It's not length, it's circumference. Conference bigger than 30, 0, smaller than 30, 0, bigger 1. Okay, so now we could have a number of these things. These are not, by the way, independent probably, yeah, because the hair is probably independent of shoe size, but neck circumference is not. Okay, let's do it differently. Hair colored, yeah. So I mean, colored hair means not natural color, 1 or 0. Historically, this would have been probably extremely strong predictor of gender. These days it's weaker, but still probably has some power. So we can now write down px given 1, px given 2 as a product, because it's independent, and each of these expressions do this. It's either pi or 1 minus pi. So we can, for instance, ask, what is the probability of a man of 0, 1, 0? Given, say, man would be class 2. So it would be, for 0, it's 1 minus kappa 1. Because the second feature is 1, it's kappa 2 times 1 minus kappa 3. We will take the kappas and get the number. If we look at the log odds, okay. So let's look at this slide. Please, in the chat, I would be happy if you confirm that you understand formula 22 and 23, else ask. Understood. Good. At least one answer.
I think I get it.
Good. Good. So, fine. Now let's have a look at the log odds. So here we wrote the conditional multiply by prior. If we take a log, they're all products here and exponentiation. So logarithms love this. The product becomes sum, the exponents become multipliers. So we get xi logarithm. This part comes from the first part in the formula with pi. Then the second part, and this minus is from the denominator. Now we'll collect stuff. Okay, it's not here, but actually we can collect stuff. I'll write it on another slide, another page. If we look at the stuff which is related to xi, we have xi is multiplied by logarithm pi I, and also with minus logarithm 1 minus pi I. So this will become wi. Pi I is a number, logarithm is number. This is a known constant. We are now assuming we know pi. So in the end, we can, so this will be a sum of xi, wi, and then there will be some number w0 here. So this 1 times logarithm 1 minus pi, that's a constant. 1 times logarithm 1 minus kappa, that's logarithm 1 minus kappa. So this w0 is the sum of logs 1 minus pi I minus logarithm 1 minus kappa I. And we get, surprise, surprise, again a linear odds ratio. So it seems that assuming linear odds ratio will be interesting because there are more than one model that fulfills it exactly, and many other approximately. Okay, we've gone through this. Now, slightly, just marginally more complex model, and I will explain this on a problem of recognizing Smarties box.
I'm sorry. I'm not sure if it's just me, but I can't see the paper.
Right. You are right. Thank you. Not intentional way of checking your. So I just, okay, this was the thing which showed how we were collecting wi times xi, and this in the end became in a vector notation wx minus w0, and these are the coefficients for the wi. So now we are at the third problem, which will also lead to linear log odds. Who knows what Smarties are, or who does not?
I'm sorry, what was the question? I didn't understand.
Do you know what Smarties are? You must know it.
Smartie, the candy?
Smarties, like type of candy. So these are like, okay, go look, Google it up, but this is okay, let's see what happens if you Google it up. In Czech, there's some lentilky. Yeah. Let's see what happens if I use my Google and try to find it. Okay, I know. Okay, so these are candies, and what the main problem is that they have. Let's assume that you are solving a problem. Whether to your shop there are two factories producing Smarties. Factory 1, which is based in Spain, and another one which is based maybe in Finland. And in Finland, these guys, so, okay, each box has blue, yellow, red, and green Smarties. And in Spain, they like yellow Smarties, so they are on average 50%, only 10% blue. They like red, 40%, and they have, okay, let's not do 40, 30 and 10% of green. Whereas the Finnish, they like blue, 50%, yellow only 10%, red, they don't like that much, 0.2, and green, this is the Finnish forest, they like it, 0.2. So the factories work like this. They produce Smarties, these small candies, with these colors, in this proportion, and then they make a random sample into the box. You get the box, and your problem is to recognize whether this is Spain or Finland. So this is statistical. So if you have, let's say a box has 10 candies, and if you see something like 3, 2, 3, 2, that box could originate from, this is our measurement. So this is x1, x2, x3, x4. Our measurements are counts. The two classes are the factories. The factories have there's a statistical relationship between the probability of certain observations and the factory. Our question is, what is the probability of 1 given x and probability of 2 given x? So now question, do you understand the statistical model for the Smarties factory?
Makes sense.
Okay, yeah. Fine. So now question number 2, which I think, do you understand formula 26, which defines the probability of a certain observation given our knowledge of pi I and kappa I? So here pi1, pi2, pi3, pi4 is the probability of the given color in a factory in Finland, or in Spain actually, and kappa 1, kappa 2, kappa 3, and kappa 4 are the probabilities in Finland. Let's say we know them, and here we see that for Spain, we'll see that if we see 3 Smarties of color blue, because blue is the first one here, it will be for Spain, it's 0.1 to the power of 3. Then we have 2, which in Spain, 2 yellow, they have a probability 0.5. Then we have the red Smartie, which is 0. I forgot what it is, 3 to the, this is 3 to the power of 3, and 0.1 for the green Smartie, which happened twice. So, and then these are the normalization factors, which play no role because they are the same for both classes. And we know that sum of pi I equals 1 and sum of kappa I is 1 are 1, because the Smartie has to be one of the 4 colors. And in every box, we assume the factor is perfect and it has n fixed. Of course, the n could be a variable. I actually don't know whether it's variable. Probably it is variable, and maybe in some fact, maybe the n could also give us some information, but we assume that it's, to keep it simple, that they are the same. So to get the log odds ratio, it's just we will delete these normalization factors, the n factorial and product of xi factorial. We get product over all dimensions, pi I xi divided by pi I kappa I xi, and if we take the log of this, it will be again a sum. It will look like sum, and then for xi we'll have just logarithm pi I minus logarithm kappa I. And here the offset is it's not there, so it will actually be w times x, where wi, this is wi. Yeah. So we have 3 completely different models that lead to log odds, which is linear. So now we're going back to logistic regression. So in logistic regression, we make the assumption that our data follow the rule that log odds is linear. So that's our assumption. We'll not make assumptions about P1 for the class condition, for the probabilities like posterior probabilities or class conditional probabilities, and we'll just say we know that a ratio is linear. Now, to simplify a little bit notation, and we'll use the same trick later on with SVM, it seems convenient not to deal with this W0 explicitly. We'll pretend that besides measurements x1 and xd, we'll have an x0, which is always 1, and this will allow us to write this affine. Actually, it's affine. It's not. I spoke about it as linear, but technically speaking, linear is what you see on the right side of 29 in these dashed coordinates, where we sort of add one measurement which is fixed. Yeah, so we will include a 0 index component with like fake measurement 1, and then we can say, okay, now it's linear in this new space. This just simplifies our notation. Okay, so now let's see what this means. If we assume that log odds is linear, then just like undoing the let's take the take this equation to the exponentiated. So on the right, we have exp wx, that's this thing exponentiated. Logarithm of exponent is just the ratio. This is just like 1 over. So here the ratio changed. Multiply. And now add these two together, the two equations 32 together. So class 1 given x plus 2 given x must be 1. There's nothing else. And that's equal to these. We have like, we substitute from 32. And in the end, we get this. Okay, we can sort of like, how did the 32 get together? So if we substitute for P1x, we get P2x exponent of the dot product x times dot x. So if you substitute this for P1 given x, you will get P2 given x is in both expressions, and 1 plus x wx scalar product, or you can substitute for P2 in this from there, and you get this expression which is shown here. And from this, we get the expression for the posteriors. That's what we announced before. So if we assume linear log odds, the posterior probabilities will have what this is called a sigmoidal function. One way to look at it is that, okay, what are we doing here? In our d-dimensional space, we have some vector w, and when we want to classify, we'll take the x, the scalar product is projecting. Let's assume that w is a unit vector. We project, and in this, on this projected direction, we'll do 1 plus 1 1 over 1 plus x. So this will be some sort of a function, sigmoidal function. So the projection here could be, so x is in d-dimensional space. The scalar product is any real number. The e to the scalar product, either with plus or minus, is a positive real. Now, and this is a factor which will send it between 0 and 1. Okay, so fine. So now we know what model we assume in logistic regression. And just a small simplification, we'll see that P1 given x and P2 given x have almost the same form up to this sign here. So we can express these equations 36 and 37 as 1, very compactly, and this will come handy. If we just rename the classes to minus and plus 1. Of course, classes can be called A or B, but if we do it like that, this K avoids an if statement. Yeah, like 36 and 37 could have had like A class B here, A here, and B here, or any other name, male, female, whatever. But if we choose minus and plus 1 convenient symbol for the class, we can complexify in here. Okay, so now we know the probabilistic model. And we'll invoke the maximum likelihood principle. So to create a logistic classifier or a classifier with logistic regression, we only have to find the W. Because once we have the W, we see the pk given x, and we know how to decide. If pk given x is greater than 1/2, that's class, okay, well, now if k is plus 1, we calculate 1 over 1 plus e to minus wx. And if that is greater than 1/2, it's class 1, else it's class 2. So the only thing which is left is how to find the W.
May I ask? I kind of got lost. The W is the strategy or the labeling or something like that?
No. W is the vector. It's a vector. So if we go back here, for instance, we showed that the log odds is a linear function in a D. Okay.
Oh yeah, of course. Yeah, I forgot. Sorry, I zoned out. Sorry.
So the W is the normal vector to the deciding plane, and it defines the hyperplane. So in 1D, it will be a threshold. In 2D, it's a line. In 3D, it's a plane, and so on. And it's defined by the W. In here, it's indeed the normal vector to the plane with W, the offset. A plane is an affine subspace. And if we add W to the representation, it's this defines a plane passing through the origin, and W prime is the normal vector to the deciding plane. Yeah. But we know more than the decision, because we also know for any X, we can calculate the a posteriori probability for both classes. So we not only know which class to go for, but what is the probability for the good one. So we also know the probability of the bad one for the one we will not decide for, and we'll also know the error for that point. So now we'll say, okay, let's give me the maximum likelihood estimate for W, given the log probability of our observations. So we'll say log P of X and K, but that's the same as log K given X plus sum of log Px. Here we just use that Pk X is the same as Pk given X times Px, and because Px does not depend on the W, when we want to maximize, we can drop it. So we'll say, okay, let's express the maximization of the conditional log likelihood. We'll say, okay, we know the form of Pk given X. That's this sigmoidal function. So log of this is 1, because of 1 over will give you the minus. So that's the minus, and we will be summing ln1 plus e to k wx. So what do we know here? We're summing over all training set. X is always the training vector. We know that. K is the class information. So that's no. And what we have to do is to maximize this sum with respect to W. So of course, it's questionable whether it's a good idea to design a classifier on the basis of maximum likelihood. Because what we want from the classifier is to make small expected error. So in the long run, we want to minimize its error rate. And there's no guarantee that maximizing the likelihood is the right way forward, because there could be maybe something which is quite likely, and on the other hand, it's performing quite poorly in terms, but okay, for large data sets and so on, we have some of the properties of maximum likelihood. So in practice, this works quite well. But that's sort of, we have to understand this is an assumption. We should not say, if I design a classifier, it is a good idea to maximize the log likelihood. Okay. So what we are left with is maximization of something in the form sum of logarithms 1 plus e to minus kwx, where the parameters which are unknown are in the vector W. Now we'll proceed in a standard way, with simplest way. If I want to look for a minimum, let's try to approach it with a gradient descent method. It's quite easy to write the gradient here. Now, maybe I'm not sure how familiar you are, or probably you might have not seen this before. We are taking a derivative with respect to a vector. That's just a vector of derivatives with respect to individual components of that vector. So if you look at 45 and you would take a derivative with respect to W1, logarithm will give you 1 over the bracketed expression. Then you will be taking the derivative of the inner function, 1 plus e to something. Okay, 1 is 0. Derivative of e to the expression is still e to the expression. And then you will take the derivative of wx as a scalar product. So it's clear that if you take the derivative of wx with respect to w, say, j, what is this? Can anyone tell me what is this expression equal to?
xj.
Xj, exactly, because that thing is nothing but y1 x1 plus y2 x2 blah 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 y dxd. So if we take a derivative with xj, everything is constant because it's not a function of xj, and the only thing which is interesting is wj xj, and this is a linear function xj. But now it's probably easy to say, well, so if I know this, let's try to say what will be the derivative with respect to the vector. So xj, x1 will, taking a derivative with respect to w1 will give me x1. Derivative with w2 will give me x2. So and we can put all these results in one vector, and it will be the x vector. Because we are not taking a derivative of this, we are taking a derivative of k times x times w. So the k will stay there. Yeah? So that's the kx here. And we see that this happens to be sort of, you see the gradient. It's interesting. The gradient is actually either plus, this k is either plus or minus 1. So the gradient of our loss function is negative or positive value of the feature itself, weighted by this 1 plus 1 e to something. So for instance, if wx is a huge number, so what does it mean to be a huge number for wx? So this is the decision boundary, which is, this is our w. Let's say this is our w, and this equation is wx equals 0. If w is a unit vector, then if you are very, very far from that boundary, this will be a huge number. E will be almost 0. This e to minus that number will be almost 0, and that will, so this will be 0, this will be 0, it will be 0 over 1. On the other hand, it could be that if you are on the wrong side, and this will blow out of all proportions, the weight will be 1. Yeah, so, but okay, look at this yourself. Now, the important thing for logistic regression is that we can look, if we are minimizing with gradient descent, in general, we have no guarantees. We'll end up with some, okay, the only thing we know in gradient descent is that if you are in some point, let's say this is my cost volume, if you are here, and this is the gradient, well, okay, this now, if we take the gradient is the direction of the ascent, so but we have the minus there. Yeah. So if you move in the direction of the gradient, there must be some small epsilon where moving from position W to small epsilon plus gradient of our energy, you must improve, will lead to improvement of the energy. This is the only guarantee you have from the gradient method. But if your function is positive definite, your Hessian matrix is positive definite, so the matrix of second derivatives is positive definite, which sort of means something like everywhere your function locally looks like a paraboloid, then your function is convex, and as a consequence, the function has a unique minimum. So it means that for convex function, gradient optimization is a very convenient method because it's quite efficient, and it has this guarantee that okay, there are some, one has to be careful in some let's say special singular cases, but let's say in general we are able to find the global minimum. So logistic regression started with the assumption that log odds is linear, and then applied maximum likelihood, and it ended up with the convex problem. So we have no problems in the optimization. And in principle, this very short code in MATLAB could solve logistic regression compared to what we'll see in some other minimization problems in other methods of machine learning. This is very, very simple. So we start with some guessed W, we choose our step size, compute the gradient, that's what we have just here, sum over all points from the training set, calculate this quantity for W's which you have chosen, this is your current value, you can calculate that, Kx is known, and we get some gradient, fine. Add the gradient here to the with some step size to the current solution. If you improved, good, adopted, and maybe we have a new position and we increase the step size. If we have not improved, we reduce the step size. And one thing which is sure is that there's up to numerical issues. Or whether we are not, when we are not at the place where the gradient is zero, there will exist a step size small enough for which we improved our energy in the gradient descent. Trivial method. So now we'll have a look at a couple of examples how this works. So we remember logistic regression, assumption of something reasonably well modeled by the assumption of log odds being linear. Adopting maximum likelihood principle of for learning, we get a very simple procedure for obtaining our classifier. Example, we have two one-dimensional Gaussian functions. They have the same sigma, different means. Exactly model one that we discussed. For this case, the Bayesian error is 16%, which means the best classifier, which happens to cut these two curves at minus 1.5, will have the error in this triangular area, and this will be 16%. So let's go. We are gods here. We know the models. Normally, when you are doing machine learning applications, you do not know the model, but here we know the model. So let's test logistic regression. Let's generate 1,000 samples from each of the distributions. So we have 2,000 samples in our training set, and let's start. So the green function shows P1 of X. This is the a posteriori probability of class 1. We don't show P2 of X because that's 1 minus this green curve. So that's sort of redundant. And let's see what we get. So we start with some initial guess 1 minus 1. And the log odds is quite off. By the way, the green curve shows that if the classifier based on the green curve would have would go for class 1 on the left of this point where it enters when the green curve intersects 0.5, and the dashed blue one would do it somewhere at +1, and it will have a very large error. It will have an error of 38%, 40%. So marginally better than random guessing, which is 50%. So now we start to iterate, and our training error is dropping. That's so what is guaranteed to be dropping is not the training error, but this energy, because the energy is minimized on a convex function using gradient descent, and we are just accepting steps which are reducing the energy. So it has to be dropped. It has to drop. The training error, which is the number of misclassified points, this is not what we optimize, but still, for this example, in the first 6 iterations, it dropped. You see that here the training error stabilizes despite the fact that we still manage to improve slightly the energy, and we end up with the curve which is almost perfect. Yeah. So this the 2-dimensional space. We are reducing the errors. By the way, you could see that maybe this zigzagging behavior at the end of our search for the optimal parameter might suggest that gradient descent is not the best minimizer even of a convex function, but in the end, in this case, we get there. And these are just like some observations. So the energy is monotonically dropping. The error, which we on the training set, is sort of dropped fast, but you see it's not monotonic, and the step size was sort of oscillating. In the end, we get a training error of 14% on the training set, and the Bayesian error is 16%. Is that possible? I just said that Bayesian error is the best possible error you can get. How come the training error is lower than this?
Overfit on the training data?
Exactly. So it's an overfit. So if we generated some other set, if it was long enough, the error of no classifier will be better on average than 16%. Yeah. So this is the overfit, but you see that the difference between the optimal classifier and the classifier that we have found is very small. Like the error is, the difference is somewhere like the intersection of the 0 is slightly to the left, but it's nothing. Yeah. So I think the true risk of the trained classifier is those 16% with some epsilon. It's almost perfect.
So, but is it bad that it overfits? So if we let it
no, it's not. Okay, we have to understand what overfit means. So this is used colloquially in 2 ways. One says our error is small, like our training error is significantly smaller than the test error. For instance, for deep networks, this is quite common, and that's not itself a big problem. The big problem is that the difference between error on training and test set is very, very different.
Yes, that's what I'm talking about. Because if we overfit on the training set, it's not generalized.
Well, but here it will. You see that here, it not well. It's not. We did slightly well. The question is, how do you measure the level of overfit? So we know that the error of this classifier found by linear will be 14% on the training set, and will be say 16.2 on the test set. But its error rate will be almost indistinguishable from the best classifier. So it did overfit, but not significantly. And what I'm saying is that the difference between the difference between the training error and the Bayesian error is not a good indicator how bad the classifier is. This classifier is near perfect, the only error it will be making, so the blue classifier will make correct decisions for everything on the left, everything on the right, and there will be a small interval around this point where it doesn't really matter. This is around the 50-50 point, that it will make a slightly different than optimal decision.
Yes, but basically what I'm asking is, if we let it run for more iterations, then theoretically we could fall to the error almost 0 on the training set, but on the test set it would go higher, right?
Like in general, yes. In practice here, no, because for this case, actually, it's interesting we don't have it on the slides, but for this case in 1D, you can find so okay, let's put it this way: the logistic regression in 1D, it's a monotonic function, so it's actually looking for a threshold. We have this curve, but in the end, the classifier will be thresholding. For thresholding, you can you can check all thresholds, really all, because you only want to put the threshold between consecutive data points, and you can find the most overfitting classifier, and it will not be too bad. Yeah? So here we can do. This is maybe an interesting thing, but let's move now. Second example. This example maybe is an example where we have two Gaussian distributions, and this time they have different means and different sigmas. Okay, I want to put it. Do what? Control 3? No. Okay, they have maybe like this. Okay, different sigmas. So now the likelihood, the log odds, is not a linear function. It's actually a quadratic function. You can think like the log odds. You'll have ln. You'll have here 1 over square root of 2 pi, 1 over square root of 2 pi. That will cancel. Sigma 1, sigma 2. They are different. So they don't cancel. E. And
I can't see what you're writing, Professor.
Aha, right. I thought I will not need this, and I will. Okay, so and then we have the ratio, so that will be like the difference, 1/2, and we'll have here x minus mean, over sigma 1 squared minus x minus me 2 sigma 2 squared, or let's put it this way, squared like this. And so this will be some logarithm sigma 2 over sigma 1, some number, some real, and logarithm of exponent will be this part, so it will be minus 1/2, and the function here. But if you look at this function, the quadratic term will be x square over sigma 1 square minus x over sigma 2 square, and this is 1 minus.
We have exactly this in the labs, by the way.
Sorry?
We have exactly this in the labs.
Still couldn't hear it.
Okay, all right.
Yeah. So the problem is the fact it will end up as ax squared, and the quadratic part will not disappear. Yeah. Okay. Good. Yeah. I see it. I have an echo, so I have to mute it. Okay. Fine. So fine. In the end, the example shows that we have something where the assumption is broken. So let's see what happens when we start working on this example. At the beginning, we start, our error is 50%, which is in some sense, the worst possible classifier, because if for two classes you have something which is worse than 50%, then you just swap. There is the output from 1 to -1, and you have a good one, better one. So here we are working. I forgot. Can I have I forgot what is the Bayesian error is 5.7%. So here we converge, to something which is approximating the left edge. Yeah? So this is a log of a quadratic function, and then we see that it completely ignores the switch here, the logistic regression. It cannot do otherwise. But if you come back to the original data, the probability of something appearing on the right is so minuscule that actually it works well. Yeah. So we got some training error of 5%, and the error will be quite similar to the Bayesian classifier, because the place where it's incorrectly on the right, where it's incorrectly classifying, is receives a very small fraction of the points, so it doesn't matter. This is an example where the model is completely hopeless. So here the linear part will not help us, and the logistic regression will do some optimization. It will reduce the energy, and the training error will be jumping around 50%, 45, 50, 51, 60, 62. It will be oscillating, and it gets nowhere. Yeah. So similar to maximum likelihood, if our assumptions are not correct, then we might or might not be lucky. And in this case, the linear log odds cannot lead to anything useful. Yeah. Of course, there are tricks how to deal with this, but we'll talk about these tricks in connection with SVMs. So just remember, when we'll be talking about lifting this, the input space, we'll talk about it in the context of SVM, but here we could do it exactly the same way. Okay, the only remaining part that I have to talk about is generalization to K classes. So this looks slightly different, but you see that we were using this. So what happens here? We have a vector W for every class. So it's sort of like, you can think about it as some sort of membership function. So this direction of W says, okay, this is the direction where my class becomes prominent. So if this becomes very, very big, W of X, presumably the others will be reasonably small in the area where I want to classify into K, and this will dominate. The bottom part is or normalization factor. This is called a softmax function because if you have some W's, W1, W2 up, and I'm doing it for scalar WD, and this is the maximum of all of those. Then if you take e to all of those numbers, or maybe e to alpha times these numbers, for some alpha, this will become much, much bigger than anything else. And if you divide each of those numbers by the sum, you will get 1, 0, 0, 0. If alpha becomes large enough, and before that you get something like epsilon 1, epsilon 2, epsilon 3, 1 minus the sum of epsilons. But it's like indicates the maximum, and it converges to like a maximum function. So it's the other way to look at it is just a normalization factor, which gives us from K projection. So we are projecting W to K, where K is the number of classes directions. Each is like the preferred direction of a given class. You get your score, and then it's normalized. Now, this looks slightly different than the softmax, which look like a single sigmoid, single two-class softmax. But if you multiply, if you express the the probability of one given X in this form with W1 and W2, just see that if we have two classes, the only thing that matters is the difference between the two between the two vectors. So we do not need, in the case of two classes, to look for two vectors because we are looking in the training, the way we use the W, it was the difference between the two. And if we have more, then we need K. Fine. Now, this is getting very important because deep nets, which are becoming very, very popular and have state-of-the-art performance, you can see them as some sort of block which takes the input and outputs some features here, and then on like a final layer, especially for deep nets for classification, yeah, then they have softmax here. So one can think about deep nets as doing some sort of transformation of the input, complex nonlinear transformation, or something called feature extraction, in a way that the logistic regression here is really highly successful. So we were saying, aha, if log odds is linear, then logistic regression is good. But now in deep nets, you are changing the input space to logistic regression so that this works. So this shows that logistic regression is used now in like a disguise in training of classification deep nets. Yeah. Okay. So let's see what's okay. Then the logistic regression, the loss function looks very similar, and we again formulate a likelihood function, take the log, which looks like sum of wk times dot product x minus this is the denominator, and then we proceed as before. So there's some example how this could look like. Yeah, so for a 3-class problem, we get quite intuitive decision surfaces, and there's a we have linear decision boundaries because of the linearity in the exponent of the logistic function. Okay, now we have like 5 minutes, which is exactly the right time. And let's write down the strengths and weaknesses of logistic regression. And now you are getting a little like, now you can't really compare too much because the only two methods of, is the nearest neighbor and logistic regression. So let's try to use your common sense, what you like and what you don't like.
Well, in regression, you have to iterate, so longer time for the computation. Okay, so this looks like a minus, but actually you'll see that this goes into the plus box because we have like optimization leads to global minimum. So you don't have to do things like many restarts. You don't have to think like, maybe I stopped my optimization early, maybe I did different parameter settings and so on. And the fact that you have like, when you say, I think what is important here, it's good that you said what you said, because like what you think, which is more like a quite, like maybe secondary school almost concept, like what can be computed in closed form is good. What requires iteration is bad. But actually maybe mathematicians were thinking like that 60 years back. And very few things can be computed in closed form. So almost everything requires iteration, and even things which you can in principle compute in closed form are sometimes calculated with numerical methods which iterate, because it's more stable numerically and it could be even faster. So, but good, you looked at the optimization part and you placed it in the wrong box, but good, because you started a discussion. Some other things, some other properties. So maybe there are so many things you can look at. So I would say that the training set size could be very, very, very big. You can use gradient descent or even stochastic gradient descent, which means the gradient actually, I do the sum over the training set and do some k times x times weight here of my example. Now this will be my gradient, say gradient of my loss function. So maybe d loss with respect to dw. Now, if I want to know the gradient and my training set is 1 million, I don't have to really sum it up over a million examples. I can take a sample of 100 and probably, and I can actually compute the statistics, it will work well, the estimate. The weakness, the obvious weakness, guys, tell me the obvious weakness. And my previous slide was somehow a mitigation of that weakness.
Well, you are assuming the linearity.
Yeah, well, the weakness is that maybe you were going the right way. I couldn't really hear you well. The weakness was that we said logarithm odds has to be an affine function. And if not, we are in deep trouble. Some other advantage, maybe, or disadvantage. So of course, this is a huge disadvantage. If I'm outside of that model, I'm in deep trouble. But you see that in machine learning, we saw this already in the nearest neighbor. Something that looks like a problem can be fixed. Yeah. So one way to look at the deep nets is to say, well, we put some transformer of the input space so that the softmax logistic regression works well on top. One more advantage is that it gives me, at least in principle, the question is how well I can estimate it, px or maybe pk of x, which means I have some sort of confidence. And also I have some idea of error rates.
We can count as another bonus that we don't have to care for hyperparameters and testing different hyperparameters and using validation sets.
Yes, so we haven't talked about this yet, but there are no hyperparameters, so this is good. Like no, well, people might not know yet what a hyperparameter is, but in fact, the only number we talked about here was the step of the gradient descent. So you didn't have to tune and fiddle with hundreds of things. Yeah, and also it's a linear classifier. So a linear classifier has good generalization ability. Yeah, we will talk about this later. So in general, it does not overfit too much. Yeah. So of course, and there's one more, I forgot, one more big problem. Another problem is that we are actually minimizing what's called cross entropy, but it's like maximum likelihood of the data of pkx, or actually pk given x. Yeah, and that's, how is this related to the error? Like if I care about the error of the classifier, I should be minimizing something
related to the error. But as the success of deep nets show, that's not necessarily some problem which hurts you if your error has the same minimizer. So here we are driving the whole thing with maximum likelihood, and still we were getting quite good results. Okay, so we are 1 minute over the time limit, I think.
Another
Fine.
minus, I think, can this happen? Can the regression fall into local minimum, not global, but local minimum?
No, but this is of the energy function, which is based on maximum likelihood. So it's a convex problem, so it will end up in, there is no local minimum.
Of course, yeah, I get it.
Yeah, so, but of course, for the error which you care about, that's a different story. But it turns out that usually if you minimize with maximum likelihood, empirically, we see that we are working well. The results are usually quite good for the error as well. Okay, okay, so fine. One more call for questions.
Yeah, I have one question.
Yes, go ahead.
Yeah, on slide number 19, I got confused. How did you remove the e to the power, like in the numerator?
I'm getting there.
Yeah, here, how did you remove the e to the power minus kw times x in the numerator?
If you multiply by e to kw dot x, e kw dot x, both the numerator and denominator, this kwx together product some of these things,
Oh, yeah.
0, 1. Then the
Yeah.
1 becomes e to kwx, and e to minus that becomes 1. And
Yeah.
then yeah?
Yeah, got it.
Good. Fine. Okay, fine. So thank you and see you next week.
Thank you very much. Bye-bye.
Thank
Thank you,
you. Bye-bye.
Professor.
Thank you. Bye-bye.